I implemented a model called Recurrent Neural Network. And what does this model do in my project is that given previous 10 days of Apple stock price, the model would output today's stock price of Apple. So here's the code. First, I load the data set, which is like I said, the Apple data set. And I'm only using close prices, which is this one. And here are a bunch of preprocessing, normalization, and splitting into training and test. And here I'm creating sequences. What does this function do is that it would create X and Y, and X, the size of X would be determined by size of sequence length, and I chose 10, so first X would be from here to here, stock price at 10 stock prices. And what would be the Y? It would be the next day, stock price of next day of these 10 days. So this one. And for the next Y, I move 1 day forward and pick another 10 days. And Y would be again the next days, and the next day for these 10 days, and the next day after these 10 days, and you keep doing this until the end of the data set. And I initialize the class called Recurrent Neural Network and I'm calling the training function. In the constructor of the class, I'm just initializing the parameters like weights and devices. And in training, first I call forward function, which is the forward propagation. And here I initialize the first hidden states. This is how forward propagation looks like for recurrent neural network. So this is the first hidden state, which is going to be this one. In this picture, it's going to be this. Then first, I have to do this calculation. It could be like this, but for the BPTT, I like to do this because it's more easier for me to calculate like partial derivatives. Anyways, so first I have to get the Z1. So this WHX is U in this picture, and you multiply with the X. This would be like one of the stock price for a day. So this is gonna be next. So you give it, so the model would have 10x because it would be 10 days of stock prices. And this WHH is corresponds to this W. And this H0 is this one. So you matmul these two and these two, and you add them up to get this H, this new H. Before that you apply activation function, but this H1 is this one, and this H2 is this one, and so on, and at last you get Y, and you take the loss. So these codes all corresponds to here, and I have to add to the vectors and return them so that later I could use them for backpropagation calculation, like here. So now we are done with the forward. I calculate the loss, which I would be logging in here. So I could just write down this code like here, but for the proper order, this is like the correct, so it doesn't really, and from here to here, all the way to here is all the backpropagation code. It's this one. So if you were to calculate gradients of loss respect to weights for hidden layer, so this W, gradients with respect to these W, by the way, those W are all the same. So yeah, you have to, I don't think I'm gonna explain this, but the difference between backpropagation with this sequential type model and the normal neural network is that because all these weights are shared between these hidden states, I have to add them to get the final. So here I'm adding all these gradients from each time step. So this one is from time step when it was time step 1, and this is when it was time step 2, and so on. And then finally I would get gradients of loss respect to WHH, and that would be this one, and I'd have to do it for these U, and which gonna be this one, and this is like biases, same, it's kind of similar to this one. And WHH HY is pretty easy to calculate because it's only contributed here, but WHH is from here all the way from here, so, and also WXH. You'd have to take into account all the time steps, so it was pretty hard to understand and to implement. And these are atom, I'm using atom optimizer, and these calculations are for it. And yeah, so after this training function, I do just evaluate. Just let me run the code. By the way, this is when I trained the model using same data set, the Apple stock price. This blue one is the true stock price. This blue line means the true stock prices, and the orange one is what model predicted. So as long as the graph looks like, the graph looks pretty good, I guess. The model is pretty predicted quite well, I guess. If I run again, it might get better, but yeah. It might take a while, but the loss from my model and from this TensorFlow one are almost same. So it's like 0.5 to the minus 0.7. This time it didn't really go well with the one with TensorFlow. I guess I should have just left what it was. I should have just kept showing you guys the first result. Anyways, so I got two prices. On the left is the true stock prices, and on the right is what model predicted. Yeah, let me run it again because it's not really yeah, this time the graph, the model has generalized pretty well. So when the graph looks like this good, the test loss is like this, and also those are the true and predicted values. So even if I use TensorFlow, the offset are pretty high. It's like they're like $10 different is on average. Like it's hard to predict. More you, it's more easier to predict. Like beginning of the data set, because of how those models are created. But yeah, it's more hard to predict when you try to predict the last bit of the data set, because the model is not forgetting, but yeah, it's kind of forgetting previous context of the data set. Yes, for this time I got test loss for this. It's better than what TensorFlow got, and the result is pretty good, I guess, if you compare it with the one from TensorFlow. But it was pretty absurd. But if I don't use Adam, things become really different. I mean, that's why I started using Adam, because it was so hard. Like you could literally see how loss decreasing now. It doesn't really decrease that much. Yeah, so that's why I started to use Adam Optimizer. Actually, this is first time trained without the Adam Optimizer and see the result. I didn't know it would be this bad. So now you know it. This also happened to one on even if you're using TensorFlow. This is the one without this SGD is like the vanilla optimizer. I mean, it means stochastic gradient descent. It means like it's the basic gradient descent technique, and also you could choose the batch size. But I think I showed you the best loss and best result in the previous one. So yeah, I guess this is it. And now I'm working on LSTM. So until I come. Yeah. Thank you.